is a good one. Okay, so given a function, often s equals f of t is the type of function that you use to represent distance. S is the distance at a specific time t. We need to define the following. The position function is simply s. And the position function tells you where the particle is. We often use particles in this situation to represent movement, motion, things like that. Where the particle is at a given time. So for example, in example 1, s of t equals t to the third minus 12t. If you would plug in a given time, it would tell you where the particle is. So let's suppose that a particle is moving back and forth horizontally. It would tell you where it is on the number line or something of that nature. Now the velocity, how would you express velocity? If somebody told you, I don't know what velocity is, how would you explain it to them in plain terms, not using speed with a direction? And how fast you're going. So if you tell somebody, if you were to describe how fast you're traveling, give me an example of, you telling somebody how fast you're traveling. You're traveling miles per hour. Miles per hour, okay? So if you're traveling miles per hour, that is a rate, is it not? So the velocity, by definition, Mr. Kozelski says that velocity is equal to, since it is a rate, it is simply the derivative of the position function. So the derivative of s, which is, f prime of t, that's velocity. And that was a good example. I think it was Marlene. I can't remember. They said it's speed with direction. So we don't talk about negative speed, but we do talk about negative velocity. That's very important. So let's think about this. If a particle is at rest, if it's not moving, what is the velocity? 0. So when we solve f prime of t equal to 0 or v of t equal to 0, those are the same, right? That's where we find where the particle's at rest. And that's important because, as I model this right now, I take an object and I throw it up into the air. There is a time where it is at rest, right? At the top. At the top, there's, for very, very fraction of a moment, it is still. It's not moving at all. And at that moment, then, if I set the derivative equal to 0, I can find maximum height. I can find when it changes direction. I can tell all sorts of things about it. It's very interesting. Particle moving in the positive direction, that would be where f prime of t is greater than 0. And the particle moving in the negative direction, so that's where the velocity is positive or the velocity is negative, okay? Because velocity has direction attached to it, we can solve it greater than 0 or less than 0 and work from there. So let's try an example. I would like to really understand example 1 and then give you a couple problems to try out of your book, and then tomorrow look at example 2, which is a little bit trickier, okay? So a particle moves according to a law of motion, s equals f of t for t greater than or equal to 0. Why do we specify t greater than or equal to 0? We don't talk about negative time in this scenario. So we start the particle in motion, and we only have positive time in that scenario. Where t is measured in seconds, and s is measured in feet. It says find the velocity at time t. If you want to find velocity at time t, what would you do to this? Take the derivative. So the velocity is equal to the derivative of the function. And what is the derivative of the function? 3t squared minus 12. So do you see why, we taught you how to do the shortcut rule. Now, taking derivatives are nice and easy. Remember how much time we used to spend doing that. So we've set that all aside. The real background and theory behind calculus, we've kind of left that. All right? And now we're going to do a lot of application and stuff like that. What is the velocity after 3 seconds? What would I do? I plug in 3. So v of 3 is equal to 3 times 3 squared minus 12, which is? This matters. Not just 15, but 15 feet per second. We have to attach a label because it's a derivative. The meaning of a derivative is that it's a rate. So we have to attach meaning to it. We took the derivative of the position, the distance, with respect to time. That's crucial. Always have to attach that. When is the particle at rest? At what time is this particle not moving at all? How would I figure that out? So v of t, which is 3t squared minus 12, we set that equal to 0. When it's at rest is when it has no velocity. If we solve that, we're solving for time. How do I solve that? Okay, I know that this is a review, but let's just identify this first. You guys are all right, but let's look at the squared piece. How many solutions are there in this situation? There are 2. There's going to be 2 times where the particle is at rest. So we need to make sure that we find both of those. Okay, so you could add the 12, divide by 3, square root it, or you could factor it, which is what I will do. So 3 times t squared minus 4 equals 0, or 3 times t plus 2, t minus 2 is equal to 0. So at time what? Negative 2 and 2. Is negative 2 in our domain? No, it is not. Negative 2 is not in the domain. So therefore, we just have one solution. It found the others, if there was negative time, but there is not. So we are just left with time is equal to 2. No. When is the particle moving in the positive direction? That's where the derivative is greater than 0. So I take the derivative, which is 3t squared minus 12, and I set that greater than 0. Now, I just got done doing this with pre-calc, and I know your pre-calculus teacher from last year. And I know that he could have spent a little bit more time talking about this, all right? And so this is crucial. You guys are going to make mistakes here if we don't look at this, okay? All right? Let's look at this in terms of a graph. Let's look at s of t, and let's look at v of t, which is s prime of t. So we're going to look at the original graph, and we are also going to look at the derivative, okay? What does this graph look like? Okay, it's an S shape. It's cubic by nature. If I want to be able to graph it, first of all, do you know what the x or the y-intercept is? 0. You find the y-intercept by plugging in 0, and you get 0. So we know we have a point here. Let's try to find some other points. Let's find the zeros of the function. Okay? If we find the zeros of this function, we would have 0 is equal to t to the third minus 12t. How do you solve for that? Factor out a t. 0 equals t times t squared minus 12. Does t squared minus 12 factor? No, but you could solve t squared minus 12 equals 0. So t squared minus 12 is equal to 0. T squared is equal to 12. T is equal to plus or minus the square root of 12. Right? 2 squared is 3. How many solutions should I have here? 3. I have 2 of them, plus or minus 2 square roots of 3, as well as 0, which I already have plotted. Okay? So, what is 2 square roots of 3? Approximately 3.4. Okay? So, I'm going to plot positive 3.4. I'm going to plot negative 3.4. And I'm going to draw my graph. I don't know how high I go or how low I go yet. That is something that we will learn in calculus in chapter 4. It's very interesting. You guys will be able to remember in pre-calculus, you guys were always wondering, Mr. Gens, how high do we draw that spot? How low do we draw that spot? That was difficult to answer. Now it's going to be easy because what's the derivative at the top spot? 0. What's the derivative at the bottom spot? 0. And so we'll just solve for 0 and we'll find those. We'll be able to do it. But that's for another time, another place. Right now, that's the function. I graph that. Okay? Tell me, looking at this function, all eyes up here, important that we make this connection because some people missed it on the test. Right here, is the derivative positive or negative? How about here? Here. Here. Okay, that's important that you understand that. So, those pieces, that's where the graph where it's positive here is where it should be. When I draw the derivative, that's where it will be above the x-axis, and where the derivative is negative is where it will be below the x-axis. Okay, so, all right. So, now let's graph the derivative. T squared minus 12 is greater than 0. What shape is that? It's a parabola that shifted down how many units? 12 units. So we could put it all the way down here, okay? Now, it would be good to find the x-intercepts. Do you know the x-intercepts of this? When you solve this equal to 0. 3 times t plus 2, t minus 2 equals 0. So you have t is equal to positive 2 or negative 2. So that's where it crosses the x-axis. So your graph is a very steep one. It looks like this. Negative 12, thank you. Okay, so do you see how these two graphs connect together? Where this is above the x-axis is where the derivative is positive. That's where this graph is increasing. Where it's below the x-axis is this middle spot. So I will draw them both in blue just to try to get one more chance of connecting your learning. That part right there coincides with this portion right here. Does that make sense? Okay, so that's very important. So when is the particle moving in the positive direction? We don't talk about the negative because we're not concerned with negative time. So when t is greater than 2, so you could write from 2 to positive infinity, that would be the interval over which it is traveling in the positive direction. So let's think about this thing. The particle takes off at time 0. Does it start by traveling in the positive direction or the negative direction? You can see from time 0 to time 2, it's traveling in the negative direction. It has negative velocity. Look, from time 0 to time 2, it has negative velocity. So it's traveling in the negative direction. So it's traveling to the left. And then, at what time does it stop and change positions? 2. And then it starts traveling towards the right. So if we want to actually illustrate the motion of this particle, here's one way we can do it, okay? It's going to start at time 0. I'm sorry, I'm throwing a lot at you that we're going to have to figure this out, but not only does it start at time 0, but where is it at time 0? 0. I look at my position function, okay? I look at my position function, which is this. At time 0, it is located at 0 on the number line. So I could start here. And it travels in the negative direction until it finally stops. And then it turns around and heads in the positive direction. So you tell me, at what time does this happen? At time 2. What is that? What is that placement? Where is it on the number line at time 2? How will I figure that out? I want to know where it is at time 2. Will I use my position function or will I use my velocity function? Position function. So what we can do is we will look at our position function here. T to the third minus 12t. We plug in 2. What's 2 to the third? 8. Minus 24 is negative 16. So this particle, again, has negative velocity right away, so it's traveling towards the left, and it goes all the way over to negative 16 on this number line. And then after that, it turns around and heads in the positive direction. So look at the question. The question is, for E, it says find the total distance traveled during the first 8 seconds. So A for the day, what is the distance it's traveled in the first 2 seconds? 16. If I wanted to figure out how far it's traveled in the 8 seconds, I would have to figure out where it is after 8 seconds. Let's figure out where the particle is after 8 seconds. If I want to figure out where it is after 8 seconds, do I use my position function or my velocity function? Position function. So let's figure out where it is at 8 seconds. 8 to the third. 512. No. Minus 12 times 8. 416. Okay. So at 8 seconds, at time equals 8, it's at 416 on the number line. So now we need to figure out its total distance traveled. So here's where we're going to tie it all together. How far did it travel here? It traveled 16. How far did it travel back to the spot? Another 16. And how far did it travel from here to here? 416. So we have 16 plus 16 plus 416. 448 feet is the distance during the first 8 seconds. It says draw a diagram to illustrate the motion. I drew it. These numbers that I put here, negative 16, 0, and 416, do those represent time? No. What do they represent? Position. Did I use the time to figure those out? Yes. Let's recap, and then you guys can practice a couple problems to try. You guys, I really need you guys to use your time wisely today and start to get your brain working on this. I was actually reading a book last night about how we actually learn and remember information. And right now is crucial as you have this that you start working on it. If you don't, we're going to lose it. So we just recap. To find the velocity, we take the derivative. To find the velocity after 3 seconds, we take that 3 and we plug it in. To find when the particle is at rest, we take the derivative and set it equal to 0. When the particle is moving in the positive direction is where the derivative is greater than 0. And we looked at the graph to find where it was greater than 0. It was helpful to look at the graphs. Find the total distance. We had to make this diagram. That's generally the hardest part for people. But trust me, you guys are coming across a lot of things this semester that at first you're going to be like, this is going to be difficult. Sometimes it takes 2 or 3 days to really get through it, and you'll be good to go. Let's try a couple problems out of our book. Let me pause this video. Tomorrow, we'll try a problem on the backside. I want you guys, page 166 at 3.4, I want you to try problems 1 and 2. Now, you guys, I just did one example, and part of our struggle will be to see how the algebra works out for some of these. The problem I have on the backside is a rational function, which we need to work through as well. But my guess is that tomorrow we're going to need to open the class with one more polynomial, allow you some time to work, and then get to the rational function on the backside. But I need you to at least give these a try. If you get stuck on one, then move to another part that you know how to do. Maybe you only know how to do A, B, C, and D for the first 2. So you just stop there, and we get questions figured out tomorrow. Please work on this now and tonight, please. Link leader meeting tomorrow morning at 7:25, my room.